Hello. In this lecture, we will start chapter 3, which is about the dynamic response of the system. We need to learn about how the system will respond before we start designing any type of controllers. First, we will talk about Laplace transform very briefly, and then discuss block diagrams, transfer functions, poles and zeros, and so on. First, about the Laplace transform. You have probably seen this in other courses. We won't go into a lot of details about that. The important point is that if we want to work in the time domain and get from a problem that is defined in the time domain to the solution, the operations will be very difficult. So what we're going to do is apply the Laplace transform on f of t, and then we'll get f of s, so we will be working in the s domain after that. We apply the operations in the s domain. Operations will be much easier in the s domain. We get the solution in the s domain, that is g of s, and then at the end we will have to apply the inverse Laplace transform to get to the solution in the time domain, g of t. As you can see, there are two additional steps involved, the Laplace transform and the inverse Laplace transform. But even though these two additional steps are there, the overall solution will be much easier this way in the S domain. At the bottom, you see the definition of the Laplace transform and inverse Laplace transform. These are the basic definitions you have seen in other courses. For example, this is how the Laplace transform of a function f of t is defined. The integral of f of t times e to the negative st from 0 to infinity. Our functions are always starting at time 0, so they are 0 before time 0. That's why we don't do this from negative infinity to positive infinity. However, we're not going to use the definitions much. Instead of that, we will use some techniques to find the Laplace transforms and inverse Laplace transforms, as you can see in the next slides. We will go over the basic properties of Laplace transform here. These properties can be easily proven by using the definition, but we will just go over the properties without proving them. What is important for us is the application of these properties. The first one is superposition. Laplace transform of alpha times f1 of t plus beta times f2 of t. Assume that the Laplace transform of f1 is capital F1. We're going to use lowercase letters to show functions in the time domain and uppercase letters to show functions in the S domain. If the Laplace transform of f1 is capital F1 of S, and Laplace transform of f2, another function, is capital F2 of S, then the Laplace transform of alpha f1 plus beta f2 is going to be alpha times the Laplace transform of f1 plus beta times the Laplace transform of f2. So this way, instead of finding the Laplace transform of the bigger function, we are actually dividing it into smaller pieces. Very useful and very simple property of the Laplace transform. Second one is time delay. If the Laplace transform of f of t is f of s, then the Laplace transform of f of t minus lambda, where lambda is a constant, is going to be e to the power of negative lambda s times f of s. We will see this property several times when we apply the Laplace transform or the inverse Laplace transform. Next one is time scaling. Again, if the Laplace transform of f of t is f of s, then the Laplace transform of f of a t, where a is a constant, will be 1 over a times f of s over a. F of s over a is nothing but f of s when you replace s by s over a. Shift in frequency. If the Laplace transform of f of t is f of s, then the Laplace transform of e to the negative at times f of t is capital F of s plus a. So in this property, we are actually going in the opposite direction. If there is a shift in frequency, instead of f of s, we have f of s plus a, then the inverse Laplace transform of that will be e to the negative at times f of t. This one is very useful in applying inverse Laplace transforms specifically. Differentiation in time. If Laplace transform of f of t is f of s, then the Laplace transform of the derivative of f is s times f of s minus f at 0 minus. Couple of things here. First, by 0 minus, we mean the time just before 0. Most of the time, this is equivalent to time 0. Second, pay attention to this piece right here. So on the right side of this equation, you see f of s, and you also see the lowercase f, which is the function in the time domain. This means if you want to apply the Laplace transform on the derivative of a function in the time domain, you will need the initial value of that function. If that initial value is 0, then the Laplace transform is simply s times f of s. If it's non-zero, you have to pay attention to this extra term and include it in your calculations. Similarly, if we apply this rule twice, we can get the second row. Laplace transform of the second order derivative of f is s squared times f of s minus s times f at 0 minus the derivative of f at 0. In this case, for applying the Laplace transform on the second order derivative, we need the initial condition f at 0 and f prime at 0. We can extend this to the derivative of order n, and that would give you the last row equation here. Laplace transform of the nth order derivative of f is s to the power of n times f of s minus s to the n minus 1 times f at 0 minus all the other terms. The last two are s times the n minus 2 order derivative of f at time 0 or 0 minus f the n minus 1 order derivative of f at time 0 minus. So we have the initial values of f and its first n minus 1 order derivatives. If all of those are 0, that Laplace transform is simply just s to the power of n times f of s. If non-zero, you have to take those into account. Most of the time we'll be only using the first one and sometimes the second order derivative. Integration in time is just the opposite of what we had in property number 5. Laplace transform of integral of f of t from 0 to t is 1 over s times f of s. This one does not have the additional terms that included the initial values, so it's simpler to use. Differentiation in frequency. Laplace transform of t times f of t is equal to negative of the derivative of f of s with respect to s. Differentiation in frequency shows up on the right side of this equation. Convolution. The Laplace transform of the convolution of two functions in the time domain, this right here, is just equal to multiplication of the Laplace transforms of each of the functions. This is what makes our calculations in the S domain much easier. If you remember the convolution integral, it's written down here. It is an integral. Finding that convolution integral is not easy all the time. So if we convert everything to the S domain, find the Laplace transform of f1 and f2, all we have to do is to just multiply f1 by f2 in the S domain. At the end, we can do an inverse Laplace transform of the result to get the time domain function. The second one, the second equation here is just showing that the convolution of f1 of s and f2 of s will be equal to 2 pi j, where j is the imaginary number, times the Laplace transform of f1 times f2. This second one is not very frequently used. We won't be using this much. The first equation is very useful. Laplace transform of convolution of two time functions is the same as multiplication of their Laplace transforms. So these were all the properties, are the important properties of Laplace transform. In this slide, we have a table, very useful table. You should have this table in front of you when you are working with Laplace transform. This table is simply showing the time functions that are very common, at least in this course, and their Laplace transforms. If you have this table and you know the properties we just talked about, you won't have to use the definitions of Laplace transform and inverse Laplace transform. You would be able to just use the table along with a couple of simple techniques that we will go over in the next slides. For example, in the first row, you see the unit impulse function, delta of t. This is delta Dirac function. It is 0 everywhere except for time 0. At time 0, it has an infinite value. Its Laplace transform is just 1. Unit step, that is the function that you probably have been using u of t to show that in other courses. In this course, instead of u of t, sometimes you might see 1 of t, especially in the textbook. In some places in the slides, I have replaced it with u of t, but the reason this notation is changed in this textbook is that we have u of t most of the time as the input to our system. So in order to avoid a confusion, u of t was just replaced with 1 of t. That is not 1 times t, that is 1 of t, same thing as u of t. It's the function that is 0 before time 0 and jumps to 1 after time 0, remains at the value of 1. The Laplace transform of this function is 1 over s. Unit ramp. This is the function that is 0 before time 0 and is equal to t. That means increasing with the slope of 1 with time. The Laplace transform of this function is 1 over s squared. Similarly, with the rest of the rows, you can simply find the Laplace transform of these commonly used functions. This one specifically is very useful. The Laplace transform of e to the negative at is 1 over s plus a. When we do the inverse Laplace transform, we will see terms like this, 1 over s plus a, very commonly. So the inverse Laplace transform of that can be obtained using this table. It will be e to the negative at. The sines and cosines will also show up in some places, but the first few rows are the most important ones. Let me erase these. Here on the right, you can also see the unit impulse function, the unit step function, and the unit ramp function we just talked about. Let's see an example. If we want to obtain the Laplace transform of the function f of t, which is equal to delta t plus 2 times u of t, and u of t here is the unit step function, minus 3 times e to the negative 2t. As I said before, all the functions we work with are only defined at t equal to or greater than 0. So that means the function is 0 before times 0. Even if that is not written, you can always make that assumption. So the function is 0 before times 0. To apply the Laplace transform on this function, first thing that we can use is to use the linearity or the superposition. Laplace transform of the entire function will be equal to Laplace transform of the first term plus the Laplace transform of the second term minus the Laplace transform of the third term, as you can see in the first row. Then we can move the multipliers, the constant multipliers, out, because Laplace transform is a linear operator, so this 2 can be moved out and this 3 can be moved out, as you can see in the second row. And then we just need to know the Laplace transform of delta, Laplace transform of step function, and Laplace transform of e to the negative 2t. From the table in the previous slide, we know Laplace transform of delta function is 1. So we just put a 1 there. Laplace transform of u of t, the step function, is 1 over s. Laplace transform of e to the negative 2t is 1 over s plus 2. If you remember, Laplace transform of e to the negative at is 1 over s plus a. So a here is 2. That means the Laplace transform is 1 over s plus 2, as you can see here. So very easily we can find the Laplace transform of that function by using the property, the superposition property, and the table of Laplace transforms. Obviously, we can apply the common denominator there to get our Laplace transform function f of s into a nice form. This is very commonly done. It's better to have our function in the s domain as a polynomial divided by another polynomial. Another example, find the Laplace transform of the function shown below. So you can see this function is not represented mathematically, but graphically. This is just a pulse. The pulse has the value of 0 everywhere except between 2 and 3, time 2 and 3. Between these two times, the value of the function is equal to 4. What we can do here is to reproduce this with step functions. So basically, we can consider two step functions. One step function that is 0 before 2 and then jumps to 1 at time 2. Another step function that is 0 before time 3 and then jumps to 1 at time 3. Now if I find the difference between these two, basically the first one minus the second one, I will have exactly what g of t is showing in the graph. Before time 2, both are 0. Between 2 and 3, the first one is 1, the second one is 0, so the difference is 1. After time 3, both are 1, so the difference is 0. So actually the subtraction of first one minus the second one would be 1/4 of g of t. As you can see, the value of g of t, the non-zero value is 4, not 1. So we just have to multiply that difference by 4. So this way, we are recreating g of t by two step functions. 4 times u of t minus 2 minus 4 times u of t minus 3. The Laplace transform of g of t, again using the superposition law, would be 4 times the Laplace transform of u of t minus 2 minus 4 times the Laplace transform of u of t minus 3. So what is the Laplace transform of u of t minus 2? From the table of Laplace transforms, we only have the Laplace transform of u of t. that is equal to 1 over s. But in the properties, in the Laplace transform properties we went over earlier, we had a property about time shift. If there is a time shift in the signal in the time domain, its Laplace transform is going to have an e to the power of as multiplied by it. So if the Laplace transform of u of t is 1 over s, then the Laplace transform of u of t minus a will be e to the negative as times 1 over s. That means if a is 2, then we have u of t minus 2. Its Laplace transform is e to the negative 2s times 1 over s, as you can see here. And if a is 3, the Laplace transform of u of t minus 3 will be e to the negative 3s times 1 over s, as you can see here. So that completes our Laplace transform for this example. We can combine the two terms, factor out the 4 over s, and write that answer as 4 over s times e to the negative 2s minus e to the negative 3s. We know how to do the Laplace transform by those examples. Just use the table of Laplace transforms along with the properties. Now, what do we have to do if we need to find the inverse Laplace transform of a function f of s? The easiest way to do this by hand is to apply partial fraction expansion. If you know how to do the inverse Laplace transform using your calculators, that is fine. But if you need to do this by hand, you will have to first apply a partial fraction expansion on your function f of s to divide it into simpler pieces, because not all of the functions in the s domain are available on the table we have. So we have to use partial fraction expansion to break it up to smaller pieces. All those smaller pieces should be found in the table, and then we will use the table to find their inverse Laplace transform. Here's an example. So we have y of s as s plus 2 times s plus 4 over s times s plus 1 times s plus 3. We want to find y of t. That means we want to apply inverse Laplace transform on this function. Obviously, you cannot find anything like this in the table of Laplace transforms. So first, we will have to apply partial fraction expansion on this y of s. For partial fraction expansion, you need to first look at the denominator and then find the roots of the denominator. In this case, the roots are very easily seen. One is at 0, one is at -1, and one is at -3. In the case that the roots are not repeated and they're all real, like this example, the partial fraction expansion is very easy to do. We will go over this one, and this would be pretty much the way we will do it. We won't be dealing with partial fraction expansion of those more complicated cases where the roots of denominator become complex ones or repeated ones. Not in this course. So all we have to do is to write y of s as a summation of 3 fractions. Those fractions in their denominator are going to have the factors that show up in the denominator of y of s. Those factors are s, s plus 1, and s plus 3. So we put those into the denominators of the 3 fractions. The numerators are constants that we will have to find values for. So you can name those anything like a, b, c, or a1, a2, a3, or in this case, say c1, c2, c3. For only one combination of numbers for c1, c2, and c3, the summation of these fractions will be equivalent to y of s that we are given in the first place. So we have to find those numbers. What you can do is, one way to do this is to do a common denominator, apply a common denominator, and get this into the form of the form showing up in the last row. In that form, you can see C1 times S plus 1 times S plus 3 plus C2 times S plus 3 plus C3 times S plus 1 shows up in the numerator. The denominator is exactly the same as denominator of the original y of s function. The denominator here is the same as the denominator here. That is because we had the same factors in the denominator of the three factors, and then when you combine them by using the common denominator, you will get obviously the same denominator as the original y of s. We need the numerator of this function to be also the same as the numerator of original y of s. So what we can do is to expand the numerator of original function and expand the numerator that we just found over here, and then compare these two. Basically compare the coefficients of the powers of s, equate them, and through that we'll be able to find C1, C2, C3. We'll do that in the next slide. If we expand the numerator of both of these functions, the one we found at the end of last slide and the original one, here's the result showing up right here at the top. So the one on the left is the one that we obtained by the partial fraction expansion form and then combined the three fractions using the common denominator. The one on the right is from the original function y of s. As you can see, both of those have s squared term, they have an s term, and they have a constant. The colors here are showing that the purple color is the constant in the numerator. That must be equal, the 3c1 must be equal to the constant in the numerator of the original function, which is 8. That gives us our first equation. We just write that down here. The red ones must be equal. Those are the coefficients of s. So 4 times c1 plus 3 times c2 plus c3 must be equal to 6. Gives us the second equation. The blue ones are the coefficients of s squared. Those must be equal as well. So c1 plus c2 plus c3 must be equal to 1. Gives us another equation. Now we have 3 equations and 3 unknowns, c1, c2, c3. We just need to solve these to find the answers, the proper answers for the constants. The last equation obviously gives us c1. It's simply 8 over 3. We replace that into the other 2 equations. Then we have 2 equations and 2 unknowns. Find, for example, c2 from one equation, replace it in the other one, and that way we will find all the 3 answers. C1, C2, and C3. The values are here. You can try to find that yourself, either by hand or by a calculator, solving those 3 equations, because something like this will happen frequently in this course. As soon as you have those constants, you can go back to the partial fraction expansion form of y of s that we had in the previous slide. C1 over s, that is this first term. We can actually separate C1 from the 1 over s. Then C2 over s plus 1 was the next term. C2 is negative 3 over 2, so multiply that by 1 over s plus 1. And the third one was C3 over s plus 2. C3 is negative 1 over 6, and multiply that by 1 over s plus 3. So we have those individual parts. Now these are simpler. As if we want to apply the inverse Laplace transform on this function, you will see how our life will be much easier. The inverse Laplace transform of y of s can now be written as 8 over 3 times inverse Laplace transform of 1 over s. Let me erase these right here. 8 over 3 times the inverse Laplace transform of this term, minus 3 over 2 times the inverse Laplace transform of this term, minus 1 over 6 times the inverse Laplace transform of this term. This is what you see over here. Now, this term right here, 1 over s, we have that in the table of Laplace transforms. 1 over s plus 1 and 1 over s plus 3, they also show up in the table. Not exactly like this, but we have a term in the Laplace transforms as 1 over s plus a. So by replacing a with 1 or with 3, we can find what is the inverse Laplace transform. So go to next line. Inverse Laplace transform of 1 over s is u of t, that is the step function. Inverse Laplace transform of 1 over s plus 1 is e to the negative 1t. You can include that u of t there or not, doesn't matter, because we always assume our functions are 0 before time 0. And inverse Laplace transform of 1 over s plus 3 is e to the negative 3t, like this term here. You can again include that u of t or not. So this last row is showing y of t, which is the inverse Laplace transform of the original function. If you don't apply the partial fraction expansion, you are not able to find the answer by using the properties and the table of Laplace transforms. So first, do the partial fraction expansion. Next, we're going to go over a very important theorem, initial and final value theorem. Initial value theorem says that the initial value of a function y of t, that means when y of t when t approaches 0, is equal to s times y of s when s approaches infinity, this term here. How is this useful? If we want to find the initial value of y of t, but we don't really have the function y of t, this helps us find that by using y of s without having to do the inverse Laplace transform. This is useful only if we want to find the initial or final value of the function. If we need to know anywhere what happens in between, then we have to apply the inverse Laplace transform first. The other one, which is more important and more useful, is the final value. Final value of a function y, that means y of t when t tends to infinity, is s times y of s when s approaches 0. This second equation is very, very important. Most of the time we already know the initial value of a function or the response of the system, but we don't know what is the final value. What happens after all the transitions happen in the response? What happens after everything settles down? Is it going to give us a constant value, and what is that constant value? Now pay attention to something here. On the right, you see an important note, only applicable to stable systems. We still don't have a very good understanding of stable systems, but it suffices to say that systems where the response, y of t, converges to a constant value. That means if the response does not converge to a constant value, we cannot really find that constant value. So if the final value is, for example, consider a sinusoidal function. The sinusoidal function keeps going up and down, oscillating. So it does not really converge to a constant value even after a long time. So it does not have a final value. If you apply this equation or this theorem to find its final value, it will give you a number, but that is certainly not the final value of that function. You should be careful about that. Another example is a function that increases with time and does not converge to a constant value. That is basically called an unstable signal. or unstable function. So again, that does not have a final value. It keeps increasing. So if you apply the equation, this formula to find its final value, the value that you will get is not valid. So pay attention to that. Whenever you want to find the final value, first find out if your signal is stable or not. If not, then you cannot really use this. You just say the signal is unstable or does not converge to a constant value. Here is an example. Find the final value of the system corresponding to that y of s given. So let's say this is the response of a system in the S domain. If we want to find y of t using inverse Laplace transform, and then find out what happens when t tends to infinity to find the final value, that takes a lot of work. You have seen that in the previous example with the inverse Laplace transform. If our only goal is to find the final value, then we can just use the final value theorem. So here, the final value can be obtained by multiplying y of s by s, and then letting s approach 0. Again, let me clear this right here and show you that this second equation is what matters for us the most. Final value theorem. S times y of s when s tends to 0 would give us the same thing as the final value of the function y of t. So we multiply y of s by s. So this s will cancel the s in the denominator of y of s. And then we let s approach 0. The answer would be 3 times 2 in the numerator and 10 in the denominator. So it's 6 over 10 or 0.6. 0.6 is the final value of y of t. Let's go to the next slide. In this one, we consider another example. The function in the S domain is 3 over s times s minus 2. Let's see what happens if we apply the final value theorem on this one. Multiply y of s by s. That multiplication of s cancels the s in the denominator. Let s approach 0, so the answer would be 3 over negative 2. But is that a correct answer? We did not check to see whether this signal is going to be a stable signal or not. This is a wrong answer. Let us do the partial fraction expansion and find the inverse Laplace transform of y of s to find the reason. If we apply the inverse Laplace transform, we will have two fractions, one with s in the denominator and one with s minus 2 in the denominator. The coefficients in the numerator, c1 and c2, after doing all the calculations, we find out those are negative 3 over 2 and positive 3 over 2. So that partial fraction expansion calculation is omitted here. After doing the partial fraction expansion, we can apply the inverse Laplace transform. Inverse Laplace transform of y of s would be negative 3 over 2 times the inverse Laplace transform of 1 over s. Inverse Laplace transform of 1 over s is the step function u of t, plus 3 over 2 times the inverse Laplace transform of 1 over s minus 2. From the table, we know that the inverse Laplace transform of 1 over s plus a is e to the negative at. A here is negative 2, so the inverse Laplace transform is e to the negative 2t. Negative signs will cancel out, so it will be e to the 2t, this term here. Now, paying attention to the second part of this function in the time domain, we will see that there is an e to the 2t term showing up in the time function. E to the 2t will increase with time, and it will never stop increasing. As you increase t, e to the 2t will increase, so it does not have a limit. It does not converge to a constant value. It keeps increasing. It is not convergent. So there is no limit value. This tells us that the result obtained from the final value theorem is not valid for this example. Now you might think, what is the point of using the final value theorem if we have to apply the inverse Laplace transform and check our answer? If we apply the inverse Laplace transform, we can easily let t approach infinity, find the answer, the final value of y of t. The answer is, we don't really have to apply the inverse Laplace transform to find out whether the signal is stable or not. Right now, we don't have the tools. We still don't know how to analyze the stability, but later in this course, we will learn how to analyze the stability of a function or a system by just looking at its S-domain function. So later we will see that by just looking at this function in the S-domain, we would understand it is not stable, so we don't apply the final value theorem on it. Here, just to show you more clearly that the signal is not converging to a fixed value, we are doing the inverse Laplace transform. Another example, 2 over s squared plus 4. If we want to find the final value, multiply by s, let s approach 0. As you can see here, if s approaches 0, the answer is 0. Again, this is a wrong answer. How do we know that? We have to analyze our y of s in the s domain. We still don't know how to do that to figure out whether it's stable or not. So in this case, we will just do the same thing as the previous example. Let's apply inverse Laplace transform and find out y of t. If you go back to the table of Laplace transforms, there is a term like omega naught over s squared plus omega naught squared. That is the Laplace transform of sine of omega naught t. So basically, sine of omega naught t will have a Laplace transform of omega naught over s squared plus omega naught squared. So whenever you see s squared plus something and a constant in the numerator, you can suspect that it's the Laplace transform of a sine function. Here, s squared plus 4 is in the denominator. So if 4 is omega naught squared, then omega naught must be 2, and 2 is what shows up in the numerator. So that is the Laplace transform of sine of 2t. That is how we do the inverse Laplace transform. Here, in this example, no need for partial fraction expansion. Now here, this is the example I was talking about earlier. If we have a sinusoidal function or any oscillating function that does not converge to a fixed value, keeps oscillating, that means it does not have a limit value. It does not converge to a constant. So using the final value theorem is invalid here. The result it gives is invalid. Whenever you are asked to find the final value of a function using the final value theorem, you need to check and see if it is stable or not, and then if it is stable, you can use the final value theorem. So after going over some basics about Laplace transform, now we want to discuss the block diagrams. Block diagrams is a graphical tool to visualize the model of the system and evaluate the mathematical relationships between the components. The reason it's good is mostly because you will see you can actually divide your entire system into smaller pieces, smaller blocks, and each of those blocks represent a component in the system. You will clearly see what is the input to that component, meaning that what is affecting that component, and what is the output of that component. and what is each component affecting. So this way, it will be easier to understand the system. A lot of cases, we will be dealing with block diagrams as the model of our system. So just like differential equations, this is another type of showing how the system works. Inside each of those blocks, we're going to have transfer functions. So basically, each of the blocks will be related, the input and output of each of the blocks will be related to each other through a transfer function in the S domain. So we'll be completely working in the S domain. It is very important to learn how the block diagrams work, which is actually the simpler part, and also how to find the transfer function of a complete block diagram, transfer function from the input to the output. At the bottom of this slide, you see an example of a block diagram, which is very common in control systems. So what we must have is a process, as I said earlier, that might be referred to as a system, process, or plant, or other names. That is basically what we want to control. The process has something that affects it. That is nothing but an actuator. Actuator is something that affects the process. For example, in the room example, the room temperature example, and the air conditioning, the entire system and the process is the room and the temperature and the air and the air ducts and everything. The actuator here would be the AC system, the air conditioning. So air conditioning affects that system, affects the variables of the system, which would be the temperature. Now, how do we tell the actuator what to do and how to affect the system? That is the job of the controller. We said earlier, if we do the open loop control, there is no need for any measurements, but that is not functional most of the time. We are talking about feedback control in this course. So we need to measure the output. That is the variable that's important for us. We do that through a sensor. We measure the output variable and feed that back to the input side. We take the difference between the reference value, which is nothing but the desired value of the output, and what is the value of the output, what the value of the output currently is. We take that difference and give that information to the controller. So the controller sees how far the actual value of the output is from its desired value, and based on that decides what to do or what to tell the actuator. The arrows on the block diagram show the direction of the flow of the signal. So pay attention to the arrows in this block diagram. In this example, you see in the first row, you have the forward path. All the arrows are pointing to the right. In the other path, which has the sensor in it, you have the arrows pointing to the left. The signal is flowing to the left, and that is the feedback path. In all the feedback systems, we have a forward path and a feedback path. As I said in the last slide, any block in a block diagram will have an input. We will consider the inputs in the S domain. It has an input, let's say G1 block has an input U1 of S, and it has an output Y1 of S. If we work in the S domain, G1 would be a transfer function, basically a function in the S domain, so G1 of S. Working in the S domain makes finding the output of that block easy. Y1 would be the input of the block multiplied by the transfer function in the S domain. The input is U1 of S, the transfer function is G1 of S. We just multiply these two and we have the output. That is what makes it easier to work in the S domain. If we wanted to work in the time domain and find y1 of t, then we would have had to find the convolution integral of u1 of t and g1 of t. We don't do that. Whenever we use the block diagrams, we work in the S domain. If we have to, at the end, we will do an inverse Laplace transform. Now we need to go over some properties of block diagrams. By this, we basically mean properties that will help us simplify block diagrams. Sometimes the block diagrams are not as simple as just one or two blocks, and we'll have to do a simplification. Sometimes we need to find the overall transfer function from the actual input to the final output. Find the transfer function that relates these two. In these cases, we need to first simplify our block diagram. We will go over 4 or 5 properties here, and first one would be the simplest one, blocks in series. If we have blocks in series like G1 and G2 blocks, you can see in this picture, the input to G1 is, say, U1, and the output of G2, let's say it's Y2. Then Y2 is simply U1 times G1 times G2. It's easy to see because you know the output of G1 is nothing but U1 times G1. That goes into the second block, gets multiplied by G2. So the final output is U1 times G1 times G2. If we want to find the transfer function of this combination, let's say we can just eliminate G1 and G2 in series and replace that by one block. The equivalent transfer function is basically y2 over u1. So we need to find y2 over u1. We said y2 would be u1 times g1 times g2. So y2 over u1 is g1 times g2. Very easy. Blocks in series, you just multiply the two transfer functions and you have the equivalent transfer function. Pay attention. Blocks in series should not have any summation point or any pickoff point in the middle. So basically the output of G1 should go directly to G2 without any signal getting taken away from that point in between. Nothing like this, or any signal getting added up to that output of G1. Those should not be there, otherwise you cannot consider those two blocks as blocks in series. The output of one should directly go to the other one without any interruptions. Second one is blocks in parallel. If you have two blocks G1 and G2 such that they have the same input, so let's say the input U of S goes to both G1 and G2, and their outputs get added up. That means here, let's say our Y of S is the summation of the output of G1 and the output of G2. Obviously, the output of G1 is G1 times U. Output of G2 is G2 times U. So if I write Y of S, which is the summation of these two, it will be G1 times U plus G2 times U. If I factor out that U, then Y of S is G1 plus G2 times U. Divide both sides by U, that will give us Y over U, which is the equivalent transfer function. It is G1 plus G2. What do we mean by equivalent transfer function? I'm sorry. Let me erase these. Again, by equivalent transfer function, we mean what if we remove this combination and replace it with one block? What would be the transfer function for that block so that these two are equivalent? The answer is G1 plus G2. So if two blocks have the same input and their outputs get added up with no interruptions in between, then they are blocks in parallel, the equivalent transfer function is the summation of the transfer functions. I talked about pickoff point and summing point earlier. I think it's pretty obvious, but you can see that in this picture. Pickoff point is where you pick up a signal and get it to somewhere else, to another block. That's what you can see on the left side. Summation point is where you add up signals. Sometimes with the summation point, we can actually do subtraction. So the signs beside the arrows that come into the summation point tell us what we have to do with this, whether it's a summation or subtraction or a combination of these. Single loop negative feedback. This is very, very important. It shows up frequently in this course because we're talking about feedback control. This is a feedback loop with a negative feedback. If we have a block G1 and a block G2 in this configuration, such that G1 is in the forward path, see the direction of the arrows, and G2 is in the feedback path like this, direction is to the left, and the output of G2 gets added up with R, which is the incoming signal, with a negative sign. So you see the negative sign here. Gets added up with that with a negative sign. And the result goes into G1. So basically the input to G1 is R minus what comes out of the G2 block. This combination is called the negative feedback loop. Negative because of this, the negative sign you see in the summation of the feedback path. The equivalent transfer function, which is the transfer function that we can put in this red block if we want to replace that feedback loop with just one single block. The transfer function of that block would be G1 over 1 plus G1 times G2. It is easy to prove this. What we can do to prove this is to start finding y. The equivalent transfer function is y over r. So what we have to do is to find y as a function of r and then divide both sides by r. So in order to do this, let us find y of s first. Y of s, the output over here, is the output of the block G1, right? So to find the output of that block G1, we just need to multiply its input by G1. But what is the input to G1? We were just talking about that summation point. The summation point is creating R minus the output of G2. So now we have to go down and see what is the output of G2. Let's take a look at the inputs to G2. G2 is taking Y as an input. So its output is G2 times Y, correct? So that now we can find out what is the output of the summation point. The output of the summation point would be R minus G2 times Y. So the signal here is R minus G2 times Y. That is what goes into G1. So the output of G1, which is our output Y, is G1 times R minus G2Y. This is written right here. G1 times the input to G1. We can expand this, write it as G1 times R minus G1 G2Y. To find the transfer function y over r, we need to have all the y's on one side and the terms that have r on the other side. So the term negative G1 G2y shows up on the right side. Let's add G1 G2y to both sides of that equation. So then we have y plus G1 G2y on the left side. Factor out y, write it as y times 1 plus g1, g2. On the right side, we have just g1 times r. You can guess the rest. Y divided by r. Just divide both sides by r. We have y over r on the left side. Divide both sides by 1 plus g1, g2. We will have g1 over 1 plus g1, g2 on the left side. So this confirms our formula. So this formula here, very, very important. You should try to remember this. It happens so often that you don't really want to just look at your formula sheet or the book every time you see a feedback loop. Try to remember this. The equivalent transfer function of a negative feedback loop is g1 over 1 plus g1, g2, where g1 is the feed forward transfer function, g2 is the feedback transfer function. Now remember, this was the result if we have a negative feedback. What about the single loop with positive feedback? You can try to redo this, but the result is very easy to obtain. If our feedback is positive here, let me use a different color. If the feedback here is positive, then the output of the summation will be r plus g2 times y. So this negative sign here will actually be a positive sign. So this will turn into a positive sign. We'll have to subtract g1, g2, y from both sides. This sign will be a negative, and then at the end this sign will be a negative. So for a negative feedback in the denominator, you will have a positive sign between 1 and g1, g2. For a negative feedback, positive. For a positive feedback, you will have a negative sign in the denominator between 1 and g1, g2. We will have that as a summary of this result in another slide later. But the negative feedback is what is much more common. Positive feedback is not very common. A pickoff point. What happens if we have to move a pickoff point in order to be able to simplify a block diagram? If we have a pickoff point somewhere in the block diagram, let's say here, and I want to move the pickoff point after the block. It is now before the block. Pay attention to the direction of the arrows. What if I want to move it after the block G1? I can do that, but if I really need all the signals to remain the same thing they were before, I need to probably make some kind of change. I cannot just simply move that pickoff point after G1 and assume everything will stay the same. So let's take a look at the signals here, U1, Y1, and Y2. U1 is the input here, is the input signal coming from the left. Moving that pickoff point will not affect that. So I have to be careful about Y1 and Y2. Not so much about Y1 because pickoff point is not affecting the signal. It is just picking up that signal, using it somewhere else. So whether I have that pickoff point before G1 or after G1 is not going to affect Y1. Remember, these lines are not like wires in an electrical circuit. The signal that is coming in this way does not get divided or divided like an electric current. So the same signal that goes into G1, the same signal goes down this way. It's a block diagram, not an electrical circuit. So moving that pickoff point certainly will not affect Y1. But how about Y2? If I move that pickoff point after the block G1, Y2 will be a different signal. Right now in the figure or the block diagram on the left, you see Y2 is exactly equal to U1, where it is being picked up. If I move that pickoff point after the block G1, I'm actually picking up this signal. What is that? It is G1 times U1. I don't want G1 times U1 for Y2. Y2 must be equal to U1 in order for my block to be exactly the same thing it was before. So what I can do is to add a block here and multiply that by 1 over G1, or let's say divide that by G1. So just put 1 over G1 here. The signal that I'm picking up is now U1 times G1. I multiply that by 1 over G1. I get the same thing, Y2, the same Y2. So you can see the summary of this on the right. All you have to do when you move that pickoff point after the block is to multiply by a 1 over G1 after that pickoff. Sometimes we have to move a summation point. In the bottom on the left block diagram, you see two signals, U1 and U2, are getting added up. Basically, that summation is U1 minus U2 because of the negative sign here. And then the result goes into a block G1 and gives the response Y1. So Y1 is G1 times U1 minus U2. Now, if I want to move this summation point after the block and still have the same output, meaning that I want to have the same Y1, what I have to do is to add a G1 block in the way of U2 signal. Let's compare the outputs. On the left, we said the output Y1 is G1 times U1 minus U2. On the right, I have U1 times G1 here, U1 times G1, and U2 times G2 down here. So the output Y1 is the summation of these two, but pay attention to the negative sign, so U1 G1 minus U2 G2, which is exactly equivalent to the output on the left side. You can think about it another way. U2 in the block diagram on the left, the U2 signal, after going through the summation, does go through the G1 block and then gets to Y1, if we want to think about it graphically. On the right, if I don't put that G1 block, if I don't add this, U2 will directly get to the summation point and to the output. It will not get multiplied by G1. So it is wrong to get U2 to the summation point directly and not multiplied by a G1. I want these two to be equivalent, so I add that G1 block. The block diagrams on the top show an example of how two block diagrams which don't really seem like they are equivalent are equivalent. Here, to show that these two are equivalent, you can find the transfer function of the one on the left, or basically find the output, let's say not y, the output y as a function of r in the block diagram on the left, and also find y on the block diagram on the right. You will see that they will be exactly the same. This means that the block diagram on the left and the block diagram on the right have the same overall transfer functions. Doesn't mean that they are exactly the same or corresponding to the exactly the same systems. They could correspond to different systems, but their overall transfer function, the input-output relationship, would be the same for these two. This is a good practice for you. You can try to find the transfer functions for those two. Basically y over r in both cases, and then compare them. At the bottom, you see another example, moving a pickoff point before a block. It's very similar to moving a pickoff point after a block. So if we have a pickoff point here and I want to move it before a block, you see the signal here has already been multiplied by G. So that's the signal here is x1 times G. If I move the pickoff point and put it here on the left side of the block G, then I'm actually picking up x1. That is not exactly the same as what I am picking up on the right side of the G block. So I can add a G block there, and then the output would be exactly G times x1 equivalent to x2. So you can see the result down here. If you move that pickoff point before the block, you have to multiply by the transfer function of that block to have the same signals. This is what I was talking about as one figure that shows the transfer function of a feedback loop with positive feedback or negative feedback. You need to pay attention to the signs here. Positive at the top, negative at the bottom. Here you see you have negative at the top, positive at the bottom. This means if you have a feedback loop with G in the forward path, H in the feedback path, with a positive feedback, then the equivalent transfer function will have a negative sign in the denominator between 1 and G times H. If the feedback is negative, then you will have a positive sign in the denominator. It's the opposite. Most of the time we have negative feedback. If the feedback is negative, you have a G over 1 plus GH as the equivalent transfer function. Again, this shows up many places. Try to remember this one. Here's an example of finding the transfer function of the system shown with this block diagram. Now you can see that by transfer function, I mean we need Y over R, output over input. The output, the input. We need Y over R. In order to start writing mathematically what each of the signals will be equal to and then trying to get to Y, we can simplify the block diagram using the simple rules we learned about. We can start with by finding blocks in series or blocks in parallel. Those are the simplest ones. So first look for these. If you don't find any of these, then you can try to look for a feedback loop. If you cannot find a feedback loop and none of the others, parallel or series, then you might have to move a pickoff point or a summation point. Here, you can see this piece here. There are two blocks. They have the same input. The same input is going to both, and their outputs are getting added up. So that is the definition of blocks in parallel. I can just replace that by one block, which is the summation of the two transfer functions, 2 and 4 over s. So look at this, 2 plus 4 over s. If you do a common denominator, you will have 2s plus 4 over s. That is what we put here. So now we look at our block diagram, at our updated block diagram again, and again try to look for blocks in parallel or blocks in series or feedback loops. There is obviously a feedback loop, but there is something that we can do before we get to the feedback loop. That is the two blocks here and here that are in series. The output of the first one goes to the second one without any interruptions, so that is blocks in series. We just can multiply the two transfer functions, and that would be the equivalent transfer function. So before getting to the final answer, let me write that here. The equivalent to these two will be equal to 2s plus 4 over s times 1 over s. So when I replace that by one block with this transfer function here, then I have just one block left in the forward path, and there seems like there's nothing in the feedback path. The feedback path here does not have a block in there. So what do we do about that? So this is the first time we're seeing this. If there is nothing in the feedback path, that means the same signal that we are picking up here is going back to that summation point in the beginning. That means if I put a block here, the transfer function for that block must be equal to 1. Don't forget this. We will have unity feedback cases like this, where the feedback path has a transfer function of 1 several times in the future, many times. So whenever you see this, do not just assume the the transfer function of this block in the feedback path is 0. It's not 0. If there was 0, there would be no path, no feedback path. It would actually break the path. But if you see the straight line like the feedback path in this example, that means the transfer function on that line is actually 1. So now if you assume there is a block in the feedback path, which is 1, and a block in the forward path with the transfer function right here, all you have to do is to use the feedback path equivalency formula that we found earlier. We said if the feed forward path is G and the feedback path is H, then and with the negative feedback, you see there's a negative sign here, then the equivalent transfer function is G over 1 plus GH. That is what we had earlier. Feed forward path is G, feedback path is H. In this case, our G is going to be this transfer function, which shows up in the feed forward path, and H is this one here, the 1 transfer function. So the equivalent transfer function to that feedback loop, which would be basically the transfer function we'll look for, y over r, because there would be nothing else left, is basically G over 1 plus GH, where G is right here, 2s plus 4 over s squared, divided by 1 plus 1 times 2s plus 4 over s squared. So that's how we come up with this right here. What you can do to simplify this, and you should do that, is to look at the bottom, do a common denominator at the bottom. So we will get s squared plus 2s plus 4 over s squared at the bottom. And then you see the top and the bottom will both have s squared in their denominators. So we can cancel that s squared and come up with the final transfer function. 2s plus 4 over s squared plus 2s plus 4. That is the transfer function from input R to output Y, is what we were looking for. Another example, this is more complicated. With this one, we can try to see what we can do if there's anything in series or any blocks in parallel. First thing I want to mention here, G2 and G5, they look like they are in series, but there's that pickoff point. We said there shouldn't be any interruptions in between, no summation points, no pickoff points in between the two blocks, so that we can consider them blocks in series. So we cannot consider those two blocks in series. That doesn't work. Blocks G2 and G6, for example. If you want to consider G2 and G6 as parallel, they do have the same input, but their outputs do not get directly added up. Output of G6 goes here, output of G2 goes into another block and then gets to the summation point. So these two are not in parallel. We cannot find anything in series or in parallel. Is there anything else we can do to simplify this? If you take a look at this part of the block diagram, you see a feedback loop. A feedback loop with a positive feedback. The equivalent transfer function for that would be, we said G over 1 minus GH, because this is positive feedback, where G is the forward path, H is the feedback path. So in this case, G1 over 1 minus G1, G3 is the equivalent of that loop. So let's take a look at that. Redraw our block diagram. This is what you should do, at least in the beginning. Redraw your block diagram every step of the work. So we take that and replace it with this block. Now we have a block diagram which is slightly simpler than the original one. Let's find something else that we can combine. we can actually find nothing else that we can combine. No blocks in series, no blocks in parallel, no feedback loops. If you want to consider this a feedback loop, again, there is an interruption in the middle. That doesn't work. This would not be a feedback loop. It's not an independent feedback loop. Now is the time that we might want to move a pickoff point or a summation point. One very useful way of doing this is either moving this pickoff point before G2 or moving this pickoff point after G2. One of these two will separate this block diagram such that we would have blocks in series or parallel or feedback loops that we can work with. So let's take the pickoff point on the left of G2 and move that to the right. If we want to do that, the signal here has not been multiplied by G2. So if I move the pickoff point after, I will have to multiply the signal by 1 over G2 to have the same thing going into G6. We will see the results in the next slide. So a 1 over G2 before G6, we actually combine that with the next step. That 1 over G2 and the G6 were in series, so we multiply those two. 1 over G2 times G6 is G6 over G2. Now there are multiple things we can do. Let me first clear that. First, you can see that these are in parallel. The two blocks have the same input. Their outputs are getting added up. So we can just add up the two transfer functions of the two blocks. These two are in series. The output of first one goes into the second one, and there's no interruptions in between, so they are in series, and we can just multiply their transfer functions. So let me clear this and see the result. After we combine these two blocks together with the blocks in series, we can also see that feedback loop that shows up with the blue rectangle around that. So we can also use the feedback loop rule that we have with that, and it is a negative feedback, and find the equivalent transfer function of that. First, let's find the equivalent transfer function of this. Multiply the two blocks, so G1, G2 over 1 minus G1, G3 would be the result of that red rectangle. And then we can combine the two parallel blocks on the right and also the feedback loop on the left. The parallel combination on the right, we can just add up the two transfer functions, as you can see here. The feedback loop on the left, we have this transfer function in its forward path, so let me call this G, and there is this transfer function in its feedback path, let me call that H. Then the equivalent transfer function to that feedback, the negative feedback loop, is G over 1 plus GH, plus because it's a negative feedback. So just replace G by its equivalent, G1, G2 over 1 minus G1, G3, and replace H by G4. That is how you will get this. The result is multiplication of the equivalent of that feedback loop and the equivalent of the parallel blocks on the right, because after we do those simplifications, we're going to have two blocks, first one, the second one. The transfer function of this first one is here. Transfer function of the second one is here. They are in series, so we just multiply the transfer functions to get the transfer function of the combination. That means we have the transfer function from input R to output y, the final answer. In this example, we had G1, G2 through G6. Normally, you have transfer functions, that means functions of S in place of any of those blocks. So it will get actually simpler than this. And at the end, you will have a polynomial of S divided by another polynomial of S. If I erase this piece at the end, you will see the final answer, simplified final answer. Now we will consider the transfer functions for systems or block diagrams that have more than one input. The only systems that we will cover in this course are single input systems, but still there are sometimes inputs that are unwanted, but we cannot do anything about them, like disturbance. In this example, you can see the disturbance D is coming in and added up to the output of G1, and that is how it affects the system and the output. How do we find the output Y in this case? We're going to use the linearity of the system and the superposition law. So what we will do is we will find the transfer function from R to Y, assuming that D is 0, and then we'll find the transfer function from D to Y, assuming that R is 0. Then the output Y would be the summation of R times the transfer function from R to Y plus D times the transfer function from D to Y. To find the transfer function from R to Y, just assume D is 0, so this is gone. And if 0 is coming to that summation, you can actually remove that summation and redraw the block diagram like this. So G1, G2, the output, the feedback path with H transfer function, and the input R is going to that summation with a positive sign, feedback is negative. The output Y is what we want. The first thing we can do here is to combine the two blocks in series. G1 and G2 are in series now that D is not there anymore. So the combination is G1 times G2. Let's write that. G1 times G2, and then we have a negative feedback loop. The equivalent transfer function for that, as we saw before, was G over G1 plus GH, where G is the forward path transfer function, and H is the feedback path. In this example, feedback is H, feed forward G should be replaced by G1 times G2. So the transfer function from R to Y, or otherwise written as Y over R, is G1 G2 over 1 plus G1 G2 H. Since this is not the actual system, we assume that D is 0. We should rewrite Y here as Y sub R, or any other notation that tells us this is not the output Y of the original system. So YR over R, this transfer function, is G1 G2 over 1 plus G1 G2 H. This is only the transfer function from R to the output, assuming that D is 0. Now, next thing we want to do is to find the transfer function from the other input D to Y and assume that R is 0. For this, I'll have to erase what we have. So erase everything. Let's first see the result. If D is 0, this is what we obtained. Now if R is 0, if we assume that R is 0, whatever goes to that summation with a positive sign is 0. So we can remove that summation on the left, but be careful with the negative sign over here if we have to include that negative sign into our calculations. So we should either put a block there with a negative sign when we remove the summation, with a -1 transfer function, or push the negative sign either to G1 or H, one of those two blocks, or put the negative sign over here. So if R is 0, what happens? This will be our block diagram. As you see, we have removed that summation in the beginning, and that negative sign is put into the H block. It could also be put into the G1 block. Now, if I want to find the transfer function from D to Y, I have a feedback loop here. In this feedback loop, this is where we have to be a little careful. In this feedback loop, the feed-forward transfer function is only G2, not G1 times G2. This is the only transfer function that is seen after the summation and before the output Y. So this would be our G if we want to use that G over 1 minus GH formula for the feedback loop. I put the minus there because the feedback is now positive. G over 1 minus GH. G would be G2. Remember, not G1 times G2. This is the block, the only block that's after the summation and before the output Y. The feedback path, on the other hand, now has two blocks. One is negative H1, the other one is G1. They are in series. It might be a little hard to see in the beginning, but obviously the output of the negative H block goes into the G1 block with no interruptions, so they are in series, even though they look like they're going into other directions. So we just multiply the two. That means H in our feedback rule would actually be the multiplication of G1 and negative H. So if I use the formula, in the numerator I'll have G2, so just put G2 in the numerator. In the denominator, 1 minus G2 times negative H times G1. So this is what we have in the denominator. The negative signs will cancel out. The answer would be G2 over 1 plus G1 G2H. This is the transfer function from D to Y. So it's because this is only considering D and not R, we should show the transfer function as YD over D, not Y over D. The complete answer of the system, Y, will be equal to the transfer function from R to Y times R plus the transfer function from D to Y times D. You can see that right here. So the overall output is the output created by R plus the output created by D. Transfer function from R to Y times R plus transfer function from D to Y times D. You can see that these two both have the same denominators and they both have G2 in the numerator, so we can factor out that common part and write it as G2 over 1 plus G1 G2H times G1R plus D. That is the complete output as a function of both inputs R and D. So remember, whenever you have two inputs, find the transfer function from one of the inputs to the output, assuming the other one is 0. Then do the same thing for the other input. At the end, you need to add up the parts of the output that are created by each of the inputs, like what we did here. Next thing we want to consider is poles and zeros. First, we'll see the definition of poles and zeros. What are poles? What are zeros? And then we'll see the effects of them. We already talked about a transfer function. In the block diagram form, a transfer function, we could use any letter for the transfer function. We normally use G or H. In this case, F is used in the block. F of S is a transfer function of that block. That means the output of that block over its input in the S domain is equal to f of s. So y over u is f of s. F of s is normally written as a function of s, which would be a polynomial of s in the numerator over a polynomial of s in the denominator. Numerator polynomial over denominator polynomial. Here, b of s is denotes the numerator polynomial. A of s denotes the denominator polynomial. The system response is obviously y equals the transfer function of that block times its input, f times u. F, we wrote it one line above as a b over a times u. Poles of a transfer function are defined as values of s for which the denominator is 0. So that means the roots of the equation a of s equals 0. The zeros of a transfer function are defined as values of s for which the numerator is 0. That means roots of this equation. Numerator polynomial is equal to 0. Solve it, that gives you the zeros. So the definition is pretty simple. You can easily find the poles and the zeros of any transfer function by just setting the denominator equal to 0, solve it, find the poles. Setting the numerator equal to 0, solve it, that will give you the zeros. Poles are normally more important than zeros. The behavior of a system is mostly determined by its poles, the value of its poles, and just a little bit of the behavior is also determined based on the zeros. For an example, consider a first-order transfer function. Let's say a transfer function is 1 over s plus sigma, where that sigma is a constant, like 5. So let's say it's 1 over s plus 5, for example. The output is 1 over s plus sigma, the transfer function, times the input u. If we want to find the impulse response means the response of the system when the input is the impulse function. Impulse function has the Laplace transform of 1. So if this u of s is 1, then y of s is 1 over s plus sigma. What is y of t then? If y of s is 1 over s plus sigma, using the table of Laplace transforms, we'll see that its inverse Laplace transform would be e to the power of negative sigma t times u of t. This u of t here is the unit step function. You can also eliminate that. This is the important part. E to the power of negative sigma t. What is the significance of this? We want to look at how the pole will affect the response. First of all, what is the pole and what is the zero of that transfer function? That transfer function in the numerator is just a constant 1, so the degree of the numerator polynomial is 0. That means it does not have any zeros. It does not have any roots, so there is no 0. How many poles does this have? The denominator is the first order polynomial of s. So if you set that s plus sigma equal to 0, you will get just one root. That root is negative sigma. Set s plus sigma equal to 0. That means s equals negative sigma. Remember, sigma is a constant, so negative sigma is the pole. Now you see that negative sigma shows up in the power of e in the y of t, e to the negative sigma t. So the pole definitely determines how that term will behave in the response. Most importantly, sigma being positive or negative plays a very important role here. When sigma is positive, the pole is located at negative side of the s-plane. Remember, the s could be complex in general, so when we talk about s-plane, that means the two axes, the real axis is the horizontal axis, and the imaginary axis is the vertical one. When when sigma is positive, s being equal to negative sigma will give us a negative number, a negative real number, of course. So it will be, the pole will be located into the negative side, the left-hand side of the S-plane. In this case, what happens to the exponential e to the negative sigma t? When sigma is positive, e to the negative sigma t is a decaying exponential. That means when t increases, e to the negative sigma t decreases. This means the impulse response is actually stable. It is decreasing and converging to zero. The other case is when sigma is negative. When sigma is negative, the pole is negative sigma, so it would be positive. And then what happens to the exponential term? E to the negative sigma t would be e to the power of a positive number times t. That means as t increases, that exponential term increases in magnitude. And it never stops increasing as t increases. So the impulse response in this case will be referred to as unstable, increasing or diverging. So you can see a very, very big difference for positive value or negative value of that sigma, or basically the location of pole on the S-plane, whether it's on the right half plane or the left half plane. Also, the magnitude of sigma will play an important role. Let's say sigma is positive. We saw that the response is going to be a decaying exponential. The larger the value of sigma, the faster that exponential will converge to zero. So that will also affect the shape of the response. Now, let's see another example. This time a second order transfer function. We look at the denominator of that transfer function. If you set it equal to 0 and solve it, you will find out that the roots are -1 and -2. So we can actually rewrite the denominator as s plus 1 times s plus 2. The poles are -1 and -2. We can, if we want to look at this, the h of t, the inverse Laplace transform of this function, we should do a partial fraction expansion. If we apply partial fraction expansion, we will get -1 over s plus 1 plus 3 over s plus 2. Now, if I take the inverse Laplace transform of this, I will come up with -e to the negative t plus 3 times e to the negative 2t. Just look at the individual Laplace transforms, go to the table of Laplace transforms, find the inverse Laplace transform of each of those terms. Now, if I draw the function h of t as a function of time, we will get the plot on the right. There are two exponential terms there. Both are to the power of a negative number times t, so both of those are decaying. That means when t approaches infinity, both of those will vanish. As you can see, the response is converging zero very fast. The terms e to the negative t and e to the negative 2t are created by the two poles. One is at -1 that creates e to the negative t. The other pole is at -2 that creates the term e to the negative 2t. So the poles determine the powers of those exponentials. Poles are both negative, as per our discussion in the previous slide. The exponentials that will be created by those negative poles will be stable. It's easy to see the powers are negative, so when t increases, the exponentials decay. This is also true for more complicated cases. The response of a transfer function, the general shape of the response will be determined by the location of its poles. As I said before, the zeros will also affect the response, but the main shape of the response will be determined by the location of the poles. So poles are very important. Roots of the denominator. Remember that. Here is in the slide where we can see the general shape of the response, the impulse response particularly, when we have poles in different locations of the S-plane. This is the S-plane with the horizontal axis being the real axis and the vertical one being the imaginary axis. any pole can be a complex number, so it can be located somewhere on this S-plane. You just have to find its real value, its imaginary value, and that will give you the point of the coordinate. Now, if you look at, let's start with the poles located somewhere on the real axis. We have already discussed this. If poles are located on the real axis, on the left half side of the S-plane, we will refer to as left half plane, LHP. Those will create stable exponentials, decaying exponentials. If the pole is further to the left, the exponential will decay faster compared to if the pole is a little bit to the right, but still on the left half plane. If the pole is exactly on the origin, it's the border between the stability and instability, that will create a constant response. If the pole is on the right side and on the real axis, the response will be an exponential that will increase with time. You can see that over here. The main difference for the poles being on the left or on the right is that poles on the left create stable responses, poles on the right create unstable responses. Now, what if the poles are complex and not purely real numbers? If you have complex poles, then they will be somewhere in the left half plane here, or here, or maybe even on the j omega axis. If the poles are complex but on the left half plane, we will still see a decaying signal. We call it decaying or stable or converging. You can see that this time the response will actually have some oscillations going up and down. Looks like a sinusoidal, but the amplitude of that sinusoidal is decreasing with time. So it is actually converging to a constant value. If the pole is on the right side, on the other hand, and if it is complex, talking about these two cases, the response will still be sinusoidal, but an increasing amplitude, with an increasing amplitude. So it's unstable sinusoidal. If the poles are on the j omega axis, that means if the poles are purely imaginary, they don't have any real part, that means on the border between the stability and instability. So the amplitude of the sinusoidals will remain fixed. So that tells you if the poles are on the real axis, pure exponentials with no oscillations. If the poles are complex, having imaginary parts, you will see oscillations. If the poles are on the right half plane, unstable answer, unstable response. If the poles are on the left half plane, stable or converging response. Also, as you go up, as the poles go up and have larger imaginary values, you can compare these two cases, for example. This one and this one. They have the same, the poles have the same real value, but the imaginary values are different. They are both obviously on the left half plane, so the response is stable, no question about that. They are both complex numbers having real parts and imaginary parts, so both have oscillations, no question about that either. The difference here would be the frequency of those oscillations. The larger the imaginary part of the pole, the larger the frequency will be. You can easily see that the period of those oscillations is smaller for this one, which means the frequency is larger. So that tells you how the response of a system would look like for location of the pole at different parts of the S-plane. Representation of a pole in the S-domain. The position of a pole or a zero in the S-domain is defined by its real and imaginary parts. So when you find a pole, in general, it would be a complex number, let's say negative sigma plus j times omega d, where sigma is negative sigma is its real part. positive j omega d or negative j omega d is its imaginary part. Positive or negative because if there is a complex pole, there's always two of them or an even number of them that are complex conjugates. Complex conjugates, complex numbers, are those that have the same real part, but their imaginary parts have opposite signs. So negative sigma plus j omega d is one pole, negative sigma minus j omega d is the other one. Negative sigma is the real part. On the real axis, you find that negative sigma, and j times omega d or negative j times omega d is the imaginary part. So you find that too. Negative sigma plus j omega d gives you this pole here. Negative sigma minus j omega d gives you the other one. We will use cross signs for showing the poles on the S-plane, and we will use circles for showing the location of zeros on the S-plane. Complex poles always come in complex conjugate pairs. We already talked about this. Now we wrote the real part of the pole as negative sigma and its imaginary part as positive or negative j omega d. These have a significance that we will see in the future slides. The denominator corresponding to a complex pair, denominator of a transfer function, that has a pair of complex roots, can be written as s plus sigma minus j omega d times s plus sigma plus j omega d. If you set that equal to 0, you can easily see the poles are negative sigma plus or minus j omega d. If you multiply this out, it can be easily written as s plus sigma squared plus omega d squared. On the other hand, the typical polynomial form of a second order transfer function is omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Here omega n and zeta are constants. This is the general form or standard form of a second order transfer function. You can see the denominator is a second order polynomial of s. So omega n and zeta are both constants. That means you will have a constant in the numerator and s squared plus a constant times s plus another constant in the denominator, if those are given as numbers. If we compare the denominator polynomial a of s that we have in the first bullet in this slide, and compare the denominator of h of s, which is the denominator of a standard second order transfer function, we can easily see that sigma must be equal to zeta omega n. This can be clearly seen because this is equal to s squared plus 2 sigma s plus sigma squared plus omega d squared. If we compare this to the denominator of h of s, we see s squared shows up in both. 2 sigma must be equal to 2 zeta omega n, and sigma squared plus omega d squared must be equal to omega n squared. That is if we want to compare that to the standard second order transfer function. Why do we need to do that? Because we're going to learn about the behavior and find some formulas for a second order transfer function, which is very common. And then those formulas and properties will be based on zeta and omega n. So whenever we have any type of second order system or transfer function, we should compare that to that standard one to find out what is the value of zeta and what is the value of omega n. Then we will use those into the formulas we have. In that case, if we compare 2 sigma with 2 zeta omega n, we will find the first equation here, sigma must be equal to zeta omega n. And compare these constants. Sigma squared plus omega d squared must be equal to omega n squared. That means omega d squared must be equal to omega n squared minus sigma squared. If we use that first equation in there as well, we can find omega d equals omega n times the square root of 1 minus sigma squared. This means if we have a second order transfer function, it has two poles because its denominator is a second order polynomial of s. The real part of the pole is negative sigma, and sigma is equal to zeta omega n. The imaginary part is either positive j omega d or negative j omega d, where omega d is written as this, omega n times the square root of 1 minus zeta squared. Zeta is called the damping ratio, omega n is called the undamped natural frequency, and omega d is called the damped frequency. Again, we will discuss about the standard second order transfer function, find results based on that. Everything will be based on zeta and omega n. So any problem that you want to solve, first you have to compare it with the standard second order transfer function, and then the rest. Previously, in rectangular coordinates, the complex poles were shown as negative sigma plus or minus j omega d. We can also use polar coordinates. This is sometimes very helpful. You know that complex numbers can be represented in rectangular coordinate system as real part plus the imaginary part, or in polar coordinates as the magnitude with the magnitude and the phase angle. For example, if we consider this complex number, if we want to find its polar coordinates, this length from that point, the complex number, to the origin will be its magnitude, and this angle will be its phase angle. So we can show the location of that complex number with that length omega n and that angle theta. We can relate omega n and theta to the real and imaginary part when the complex pole is shown in rectangular coordinates using this. So if we want a rectangular coordinate system, we can find the real part and the imaginary part using these two formulas on the left. If we want the polar coordinate system, we can find zeta and we can find omega n using the two formulas on the right. Remember that omega n would be the magnitude, the phase angle will be theta, which is sine inverse of zeta. So basically sine inverse of this, sine inverse of sigma over omega n. Speaking of a standard second order system, here we can take a look at possible unit-to-step responses to a standard second order system. By unit step response, we mean the response of the system when the input is a unit step function. The output could be one of those black lines that you can see here. Depending on the value of zeta, the response will be determined. The shape of the response will be determined. For example, if we have the transfer function has a zeta equal to 2, we have that bottom line as the response, which is a pure exponential that rises up to the final value with no oscillations. It is obviously stable. It does not have any oscillations. In other words, it does not have any overshoots. The other one is to look at is 1. When zeta is equal to 1, the response is still an exponential that goes up to the final value with no oscillations. That is the largest value of zeta that gives a response with no overshoot. If zeta goes anywhere below 1, like 0.8, 0.7, or any other ones that you can see, the response will have some oscillation, so obviously it will go above the final value and then back below and then converge if zeta is somewhere greater than 0 and less than 1. If zeta is equal to 0, then you will see pure oscillations going up to twice the value of the final value, coming back down to 0, going up, down, and this continues. The amplitude of the sinusoidal will not decrease. So for the system to be stable, obviously we need a zeta greater than 0. Between 0 and 1 will create a response with some overshoot and oscillations. If zeta is greater than 1, no overshoot will be seen. An example, find the correlation between the poles and the impulse response of the system with this transfer function given. You can see that the denominator is a second order denominator. If we want to compare this with the standard second order transfer function, we don't have to worry about the numerator as much. Just compare the denominator of this with the denominator of a second order standard second order transfer function. The standard second order transfer function written down here. Compare the denominator of the standard second order transfer function with this. Equate the coefficients. S squared in both. Then we have 2s in the in this example's transfer function, and 2 zeta omega n in the standard second order transfer function. We equate these two. The constants in the denominator are 5 and omega n squared in this example's transfer function and the standard second order transfer function respectively. So we equate 5 to omega n squared. Again, don't worry about the numerators. Just get your equations from equating the denominator coefficients. So omega n squared equals 5. That means omega n is the square root of 5. 2 zeta omega n is 2. That means zeta is 1 over omega n. We already have omega n from the first equation, so that gives us zeta as well. The exact response can be obtained from that transfer function with the poles that can be found to be at -1 plus j2 or -1 minus j2. You can find that by setting the denominator s squared plus 2s plus 5 equal to 0 and then solving that. Two complex poles, as you can see, complex conjugate ones. The real part of the pole is -1. As you can see, and that means the pole is on the left half plane of the S-plane. So that means we are expecting a stable response. It does have an imaginary part, so the response will have some oscillations, but the oscillations will decay and the response will converge to a fixed value. If we do a partial fraction expansion on this one, we will actually make it a little bit more difficult than what it is. But instead of that, we can rewrite our transfer function h of s into the summation of these two terms. And for that, what we are doing here is basically having s plus 1 in the numerator, and then that multiplied by 2 will give us 2s plus 2. The actual transfer function is 2s plus 1. So we subtract the 1 over s plus 1 squared plus 2 squared. We subtract that part. Why we do that? Because if we go to the table of Laplace transforms, we will see this term over here where there is an s plus a in the numerator and an s plus a squared plus omega squared in the denominator. That's why we did that. So now that we have s plus 1 over s plus 1 squared plus 2 squared, that means a is 1 and omega is 2. So the inverse Laplace transform for that will be e to the power of negative 1t, times cosine of 2t. So if you look at this. Similarly, for the second piece, the second fraction that you can see there, 2 over s plus 1 squared plus 2 squared, you can take a look at this other line in the table of Laplace transforms, omega over s plus a squared plus omega squared. So if you compare this with this right here, you can see that a must be equal to 1 and omega equal to 2. Its inverse Laplace transform would be e to the power of negative 1t times sine of 2t. So the inverse Laplace transform, and the answer would be 2 times e to the negative t times cosine 2t minus 1/2 e to the negative t sine of 2t. As we expected, we see the sinusoidal signals. And there are the exponentials with the negative powers. That means that will decay the response. We said the response must be stable, but with some oscillations. 2 damped oscillations. If we want to do this with MATLAB, we can just get the impulse response, use the impulse command. Just like the step command, with the impulse command, we have to give the two arrays in parentheses. The first one gives the coefficients of the numerator, which are 2 and 1. 2 is the coefficient of s, and 1 is the constant. And then coefficients of the denominator, you have to write the denominator in the expanded form, and then pick the coefficients from there. We had s squared plus 2s plus 5, so the coefficients are 1, 2, and 5. We put those together, run the impulse response. That will give us the impulse response of that transfer function, meaning that if the input to that system with that transfer function is the impulse function, its output is what is plotted there by MATLAB. You can clearly see a part of the sinusoidal, but it decays very fast. The sinusoidal is still there even in this part after 4 seconds, but we cannot really see that because the amplitude gets very small very fast. But as you can see, the effect of poles on the response can be seen. Most importantly, the pole having a positive real part or a negative real part affects the stability or instability. The imaginary part of the pole will affect whether there will be any oscillations or not, and how large those oscillations are, or how what would be the frequency of those oscillations.